Hello, everyone. So welcome to our live stream. Just give me 1 second to make sure that everything looks fine here. I'd hate to start recording and there's no sound. Um, okay, there seem to be three people in the chat. So as I explained in the email, I'm just going to review for the test. I don't know how long this will take, probably like an hour and a half or so. And if you're not watching this live, that's okay. If you are watching it live, then you can ask questions in the text chat. And if you want me to do extra problems of a particular type, that's fine. Otherwise, I'll just continue through and basically just discuss what's on the test. Okay. What does the test cover? Everything that we've done up to this point in the course, and it seems like a lot of material. In a sense it is, but a lot of the stuff like the binary arithmetic, binary logic, by this point is pretty easy. I mean, when you first see it, it's very, very strange, and once you get used to it, you go, well, this is kind of trivial. Okay. And I should just say something also about the course beyond the test, and that is that the course is going to get a lot more practical from this point on. This was more or less like just the like what exactly is computer technology, and I kind of answered that question. Okay. But from this point on, people are going to say, well, why am I taking a course in computer literacy when you're studying this much in depth about how computers work? Well, there's this stuff that, like I said, that's coming up is going to be like much more hands-on stuff that you can make use in your day-to-day life. But I think it's good at one point in your life to just see, like, what is this stuff? What is this technology that's all around us? Okay. So let's begin. I started the course off at a very kind of strange starting point, and that is we covered technology as a history. Okay, really fast. Like I think I only spent like maybe an hour and a half on these different technological revolutions that have occurred. And human beings, Homo sapiens, have been on this planet for about 200,000 years. Okay, I not my field, so I don't know for sure. People debate this all the time, but that's not a long time. Okay, considering that the Earth has been here 4 billion years, and dinosaurs, you're going back 300 million years. Okay, so it was fairly quick, but only 12,000 years ago. Most of that time we were hunter-gatherers. I didn't put that down here, but you should know about hunter-gatherers. Okay, so what hunter-gatherers do is exactly that. They chase after their food. They hunt their food, and they don't grow plants. They find already grown plants. That's what the gathering is. Okay, and we did that from 200,000 years ago when the species first started, up until just 12,000 years ago, and then we had probably the most important thing that ever occurred. If this hadn't occurred, I mean, I don't know. I don't know I guess we'd be still hunter-gatherers today, but that's the Neolithic Revolution. That's basically we learned how to farm. It's only 12,000 years ago, okay? Not that long ago, all right? And then, about 3,000 BC, so about 5,000 years ago to about 1,000 years ago. To about from 5,000 to 3,000 years ago. So that's from about 3,000 BC to 1,000 BC was the Bronze Age, and then beginning at about 1,000 BC was the Iron Age. Okay, and remember, bronze is a mix of copper and tin, and what you do is you simply can melt copper out of rocks in a fire. You can melt tin out of rocks in a fire. You mix them together and you make bronze, and bronze is stronger than copper by itself, and it's stronger than tin by itself, and so it's strong enough to do stuff with it. Okay, like to make weapons and knives and things like that. Okay, so during the Neolithic, even though we knew how to farm, we were actually using stone tools, and then beginning with the Bronze Age, we started to use metal tools, and then the Iron Age was even better. But for the Iron Age, you can't just melt iron out of rocks. You have to use a extra hot fire, and so you needed these bellows to make the fire extra hot. Those were they basically squirt air out to get air through a fire so that it gets hotter than normal, and that's how you can make iron. Okay, then from about 1,000 BC until just about 300 years ago, I mean, there was growth in technology there, but there wasn't anything really big. Then the Industrial Revolution came, and that's when we built mechanical muscles, as CGP Grey calls them, or you might call them machines, basically just machines. Okay, and replication, like a lot of the things that you see now, like the fact that all of your chairs look the same, all of your computers look the same, all your cars look the same. Well, not exactly the same, but every car is made basically on a construction line, and they're all identical. And that kind of replication, that automation of the construction of goods was something that began during the Industrial Revolution. Okay, and it's still with us, obviously, but we're now probably in what you would call, what history might call, the information age. So that's happening right now. Okay, each one of these ages, each one of these revolutions totally changed the way we live, and that's one of the things that you can say about technologies. I guess that's this point down here, that when a technology enters your society, you really can't live without it. I mean, it would be imagine living without a car. Imagine living without a phone. Imagine, going back to living like hunter-gatherers. We couldn't do it. I mean, you would survive. We just, like, we naturally farm because it's just part of the way we live, and we expect farming, and that's how our grocery stores are filled up. Okay, so once a technology enters a society, you really can't live without it. Okay, and the other thing about technologies is they're kind of transparent to us, meaning that we just use them without thinking about how they work. Like that's one of the things I wanted to show you in this course. Okay, and I did, is how they work on the inside. Okay, now we're going to set that aside, like I said, but now you got an idea of like how these things work on the inside, and that's our information age. Okay, the other thing I didn't put down here is that it's a new technology is not always good. So let's write that down. A new technology brings both good and bad. So there's bad stuff that comes along with the good. Okay, so with the Neolithic revolution, yeah, you could grow food. It's much easier to get food that you grow. Okay, but at the same time, we started living with animals and we got diseases. Okay, and with the Iron Age, okay, the Bronze and Iron Age with metalwork, warfare got even much more serious. Okay, and so things are getting more and more serious. The Industrial Revolution is really interesting because it was recent. Uh, um, Enormous amounts of unemployment. Okay, because remember, the mechanized looms put people out of work. Okay, the textile workers out of work. There was a good thing that came out of it. It went from we went from having to most of society having to be farmers to now only a very few portion of people have to be farmers. A very small fraction of society have to be need to be farmers, and the reason for that is because we've got tractor trailers or tractors, sorry, that we can work the soil with, and so a lot of our farming is automated, and that made the human population explode. Okay, I think before the Industrial Revolution, we were well under 1 billion people, and now we're like, we're pushing 8 billion people. We'll reach 10 billion in no time at all, and that's because of not just better farming techniques, but that's a large portion of it. So the Industrial Revolution introduced a population explosion. Okay, but at the same time created horrible amounts of unemployment. Okay, so there's both good and bad that come out of these revolutions. Okay, so what do you need to know? Well, you need to know like what happened during each one of these. Okay, and you generally need to know the lesson that we're getting out of this history. And the lesson is that, one, we just use our technology without thinking about it. That's what we mean by transparent. Okay, you don't really think about how your phone works. You just use it. Okay, the other thing is that once the technology is in your society, you gotta use it. You could try living without it, but then you're living like a primitive lifestyle, okay, which some people like, but I don't think a lot of us could do it. Okay, and new technologies, when they enter our society, they bring good, but they also bring bad as well. Okay, that's enough for the technological revolutions. If you understand that, then there's just a few questions on that, multiple choice, and that's it. Okay, so let's see here. If you have any questions, just type them in the chat. Okay, so got 3 people watching. There's about a 30-second delay. So if I look in the chat and I don't see a question, I'll go back. I may miss your question, but that's okay. I'll catch it later on. Okay, so just look again. Yeah, I don't see anyone having asked any questions in the chat. Let's move on. So the next thing we talked about were Roman numerals versus Arabic numerals, or just how numbers work. That was important because we have to get the binary numbers. Without the discovery of binary numbers, we would not have been able to have computers. Okay. Now I don't want to go how each of those systems work, but the most important thing you need to know is that with Roman numerals, okay, it's easy to count to up to like a few thousand. So it's easy to count to several thousand, which is, I don't know if you want to call that a big number or not, but it's a fair size. It's not like remember before that you could use sticks. Okay, like with sticks, if you're up to about 20 like little markings, then you start to lose track of like how big your number is. Okay, but with Roman numerals you can count up to several thousand, so that's good. Okay, that's good that you can count up to several thousand, but bad, can't do arithmetic easily. I'm sure they had ways of doing it, but can't do arithmetic easily. Okay, if we if all we knew were Roman numerals today and we had all the other technology, I don't know if we could actually, but if we only had Roman numerals, we wouldn't be able to build computers based on Roman numerals. Okay, we could barely get our heads around how to add Roman numerals. What would the rules be? It's never mind building a machine that does that. Okay, now Arabic numerals, if you remember, that's just the ordinary numbers that we use now. We call them Arabic numerals because they came from the Arabic world, but Arabic numerals, and they're good. They're good in both ways. Okay, you can count to more than several thousand. You can count to infinity. Okay, and you can do arithmetic easily, and so they're good on both accounts. All right, so that's why we still play with Roman. We still I don't know, like on the side of a building you'll see Roman numerals or something like that. Okay, they're ornate, so we still use Roman numerals, but we don't use them to do any kind of accounting, any kind of math or anything like that. Okay, we use the Arabic numerals, and that's why, because otherwise we just wouldn't be able to do arithmetic with them. Okay, now the Arabic numerals, when they were first introduced, that was the decimal system. Okay, and that means you've got 10 symbols, 0 all the way, I won't write them all down, but 0 through 9. Okay, if you include the 0 symbol, then that's a 10th symbol. Okay, so there's the symbol 0 through 9 is 10 unique symbols. That's why it's called the decimal system, because decimal means 10. Okay, it's actually from Latin. Decim in Latin means 10. Okay, so 10. But there are other systems. You say, well, why did we have to choose 10? We chose 10 because 10 fingers. Okay, it's easy to count in 10 fingers. But you could do binary, and that's what we did. But binary has just 2 symbols, 0 and 1. All right, and that's great for computers. And the reason it's great for computers is now is those transistors, they're little switches. They're either on or off. So off is like 0, on is like 1. So if you say what's inside a computer, transistors. Say, well, what's a transistor? Little tiny switches. That's it. There are billions and billions of tiny little switches inside a computer, and as they switch on and off, they'll switch on and off other switches, and so there's this kind of a cascade of switches switching on other switches and so on. And basically, that's computation. That's how a computer works. Okay, and you saw that with the adder. Okay, but because computers just work with these switches that are either on or off, you have to use binary. That's it. That's why binary is used with computers. Okay, now that's why binary is there, but you need to know it for everything that we're going to do in the remainder of the course, because when we're going to do the next topic after the test is going to be you buy a USB drive, it says 64 gigabytes. Like, what does that 64 gigabytes mean? I kind of answered that question, but we're going to be doing a lot more of that after that. So or you get an internet package, okay, and it says this internet package has a 100 megabit per second download speed. What does that mean? So everything is in terms of bits. Okay, so that's why it's important to know binary to understand all of the fundamentals of computers. Okay, but there's also Octal, and I don't expect you to work with Octal, but I just expect you to know that it exists. And there the symbols are 0, 1, 2, 3, 4, 5, 6, and 7. Okay, and so there's basically 8 unique symbols. 8 unique symbols, Octal. Okay, and then there's the other one, which is hexadecimal. And every once in a while, you'll see a hexadecimal number. Later in the course, when I do the internet, we'll see hexadecimal numbers. And there, you're going to have everything from the symbol 0, 1, 2, and then I'm going to skip them. You get up to 9. You go, am I done? No, you're not done at 9 because that's only 10. You're also going to have A, B, C, D, and E, okay? And is that, let's see, that's 10, 11, 12, 13, 14, 15. No, one more, E and F, okay? Is that right? 10, 11, 12, 13, 14, 15, 16. No, yeah, there's an F. Yeah, okay. So anyhow, sorry about that. So 16 unique symbols. And you go, A, what's A? It's this much. Okay, I know that we say 10, but in hexadecimal, it's this many fingers, okay? Because you don't stop at 9. You keep going past them. Okay, again, I don't expect you to work with hexadecimal, but you will see it. And so when you see a number that's in hexadecimal, you should go, oh, that's a hexadecimal number, even if you don't do its values or convert it or anything like that. Okay, so great. Okay, like when we look at IP version 6 addresses, well, you'll see hexadecimal numbers there. Okay, and I'll just tell you they're hexadecimal. We won't have to convert them. So there it is. Okay, so what do you need to know about decimal, binary, octal, and hexadecimal? Just that. Okay, nothing more. Okay, I guess one more thing, but it's kind of obvious. If I have a decimal number like, I don't know, like 365, like that. Okay, what does 365 mean? Well, the columns mean something. That's the ones column, that's the tens column, and that's the hundreds column. And so you could interpret this as 5 ones plus 6 tens. Okay, let's put some spaces in there like that. Plus 3 100s like that. Okay, I say it's kind of obvious because I mean, you know that like that's the ones column, so that means you got 5 ones. That's the tens column, so it says you've got 6 tens, and that's the hundreds column, so you got 3 100s. Okay, like that. All right. Okay, good. Hopefully that's easy so far. Let me see here. Oh, we got 4 people now watching. Okay, so let me just chat in here. Any questions so far? Otherwise, I'll just continue. I'll take a sip of my tea in the meantime. All right, let me continue. I don't want to waste your time. Okay, now this is where it starts to get interesting. A little bit more mathematically demanding. I expect you to work with binary numbers, okay, for obvious reasons. They're the foundation of computers, and you have to be able to convert them. So the things you're going to have to be able to do is convert them. Okay, so convert binary to decimal, not the other way around. I will never give you a decimal number and tell me and say to you, what's the binary? I'll give you a binary number and expect you to give me the decimal. It's not that hard, but you got to limit how much you're going to do. You have to be able to add them and multiply them. Okay, now I did show you subtraction and division, but you don't have to do that. I just show them to you to say, yeah, it's possible, but not that you have to do them. Okay, so converting binary. Now binary numbers, like here's a question I've asked in the past. Okay, is that a binary number? Well, it definitely isn't. So how do you know that's not a binary number? Because binary numbers are only made up of ones and zeros. And what do you see in the middle of this? You see that 2 there. And so this cannot be a binary number. Okay, so binary numbers are only made up of ones and zeros. All right, so let's get rid of that 2 for a second. And let's say, okay, let's convert that. Now, the way this works is, you've done probably a lot of these, so this probably seems trivial to you now, but this is a review, so let me show you. This is the ones column right there. So this one is in the ones column. The next one over is in the twos column. The next one over is in not the fours column. Okay, and the next one over is not at the 6. Some people make a mistake and they'll say 6 here. It doubles every time. So the last one was 4, so this is the 8s column. This is the 16s column. Let's put another space in there. Okay, like that. 16s column. Oops, there we go. And it's not lining up right. Okay, it's good enough. Okay, and what's twice 16? Well, 32, right? So this is the 32 column. Okay, and this one is going to be the 64 column. I'm having troubles aligning everything here. Okay, good enough. All right, and then the last column here is going to be twice 64 is 128. 128 like that. Okay, so that's the 128 column. All right, so that 1 is in the ones column, so you just say, okay, I have a 1. All right, that 1 is in the twos column, so you say, okay, well, I also have a 2. Okay, and I should say on this side, on the left-hand side, that's the binary number. On the right-hand side of the equality, that's the decimal number. Okay, and I have a 4 because there's a 1 in the fours column, so plus 4. And there's no 8. Okay, so skip the 8. All right, there's a 16, so you got a 16 here like that. And a 1 in the 32 columns means I have a 32. How many 64s do I have? None, because there's a 0 there. And finally, I have a 128 like that. Okay, 128. And let me just bring up my calculator. Obviously, you can use calculators during the test. It's open book, and you can use calculators during the test. Okay, so what's that equal to? That's equal to 183. All right, so this binary number here, 1011. Oh, I think that's, yeah, you can't see the 183. 1 second here. Let me just scroll that down. Okay, let me do that again. So the binary number 10110111 is the same as 183. And very quickly, 1, 2, and 4. Okay, so 1 plus 2 plus 4, no 8, plus 16 plus 32, plus 16 plus 32, no 64, and then plus 128. No 64 and then plus 128. Okay, so just go through the columns like that. And the only other mistake I've seen people make is, like I said, sometimes they'll say, well, you know, it goes 1, 2, 4, 6. You know, like they'll add 2 every time. No, it doubles every time. Okay, so you know, twice 8 is 16. Okay, and then twice 16 is 32, and then twice 32 is 64, and then twice 64 is 128. Okay, there you go. That's how you convert. I don't want to do a lot of these because, you know, maybe I'll do just one more because they're pretty straightforward. And I don't know. Let me just do one more quick one here. 100100011. Okay, let's do that one. All right. So that has a 1 in the ones column, and it has a 1 in the twos column. Okay, that's the fours column. There's no 4, there's no 8, and there's a 16. Okay, so once again, you start with the right side, okay, of the number, and move towards the left. So there's a 1, there's a 2, no 4, no 8, a 16, no 32, no 64, and a 128. Okay, I think I got that right. I'll check in just a second. Copy. I'm just letting my calculator do the 147. Okay, so let me just check to make sure that's right. 100100011. It is. Okay, so there's another example for you. Okay. All right. I think that's good enough for binary conversion. I don't want to do too many of them. I think I have 4 on the test, binary conversion, and they start really simple with just like I think like maybe 4 numbers, and then they get pretty long. Okay, so all right, let's go on. Okay. All right. So binary addition. Okay. So before I actually show you binary addition, okay, let me just mention that whenever you're adding 2 binary bits, and that's like, you know, like when I say a bit, that's a bit and that's a bit. So like 1 binary digit. So there's only 4 possibilities with 2 bits. 0 plus 0 is equal to 0. 0 plus 1 is equal to 1. 1 plus 0 is equal to 1, and 1 plus 1 is equal to 10, like that. Okay, so when you add 2 bits, you can either have a carry of 0. Actually, let me write in the carries there. Okay, usually we don't write the leading carry, but I'll put them in there. You see that for these ones, the first 3, there's no carry. Or there's a carry of 0, you could say. Okay, so there's no, and then there's a carry of 1. So whenever you do 2-bit addition, you can either have a carry of 0 or a carry of 1. Okay, and you just have to keep that in mind. Okay, even with 3-bit addition, maybe I should add that too. So with 2-bit addition, you have the possibility of carry of 0, 1. Even with 3-bit addition, I'll show you that in just a second. Even with 3-bit addition, you can have a carry of either 0 or 1, okay? And what's 3-bit addition? Well, it's the same as these, but you could also have 1 plus 1 plus 1. And if you do 1 plus 1 plus 1, it's 1 carry 1, like that, okay? So it's like 1 carry 1, okay? So either 2-bit addition or 3-bit addition, you can have a carry of either 0 or 1. And I mentioned that in contrast to multiplication, because when you do multiplication, there is never a carry in multiplication. I'll show you that in a minute. But with addition, there can be a carry of 0 or 1, but with multiplication, there is never a carry, okay? So let's do a long addition. So I don't know, I don't want to make this too long, but let's 1 0 1 1 0 1 1 0 1, like that. And let's add that to 1 0 0 1 1 1 0 1 1, like that, okay? Hopefully this will give us something interesting. All right, okay. And let me see if I'm going to get all the possibilities here. No, I will not. Hold on. There we go. Okay. Sorry about that change, but I want to make sure that I get all the different possible situations of 2 and 3-bit addition. Okay. So how many bits are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is a 9-bit number plus another 9-bit number. Okay. So let's go ahead and add those. So you start with the left-hand side. You go 1 plus 1. So 1 plus 1 is 0 carry 1. So down here, below the line, you write 0. Okay, so 1 plus 1 is 0. And then you have a carry of 1 up here. And we'll write the carries up there like that. Okay, so 1 plus 1 is 0 carry 1. And then you're in the next column. 1 plus 1 plus 1 is 1 carry 1. Okay, and then 1 plus 1, and the 0 you could just ignore, but just like 1 plus 1 is 0 carry 1. And now you got 1 plus 1 plus 1, which is 1 carry 1. Okay, and now you got 1 plus 1, which is 0 carry 1. And now you've got 1 plus 1 plus 1, which is 1 carry 1. Okay, 1 plus 1 is 0 carry 1. And then 1 plus 0 is just 1 with no carry. Lots of carries in this one, okay? But this last one had no carry. 1 plus 0 is just 1 with no carry. And then 1 plus 1 is 0. And then the last carry, I guess I could write it over here, but, there's nothing else. There's no column further to the left, and so there's just a 1 over there like that. Okay, so there we go. Actually, yeah, it's good enough. Okay, so there's your answer. All right. And let me just go through it very quickly again. Okay, you start with the left-hand side here. I'm sorry, you start with the right-hand side here. Okay, so you start with the right-hand side and you move to the left. So you do 1 plus 1 is 0 carry 1. Okay, and you go 1 plus 1 plus 1. Let me do that again. 1 plus 1 is 0 carry 1. And then you do 1 plus 1 plus 1 is 1 carry 1. And then 1 plus 1 is 0 carry 1. And then 1 plus 1 plus 1 is 1 carry 1. And 1 plus 1 is 0 carry 1. And then 1 plus 1 plus 1 is 1 carry 1. And 1 plus 1 is 0 carry 1. And 1 by itself is just 1. And then 1 plus 1 is 0 carry 1. And we're done. Okay? And since we're practicing converting, let's just do that. I hope I'm not boring you here, but if you find this easy, that's good. That means you understand it. So here I have a 1, a 2, a 4, and an 8. So that's 1 plus 2 plus 4 plus 8, like that. Okay, so that's a 1 plus 2 plus 4 plus 8. No 16. A 32 and a 64. So plus 32 plus 64. Okay, so let's start again. 1, 2, 4, 8, 16, 32, 64. 64. No 128. And after that, it's 256. So plus a 256 there, like that. All right. And then the next number is a 1 and a 2. All right. So we got a 1 and a 2. Skip the 4. Okay. So a 1 and a 2, no 4. An 8 and a 16 and a 32. So an 8. Oops, I forgot the 16 plus 16 plus 32. I don't know if there's a 64, so let's get rid of that. Okay, so let's see here, a 1, a 2, no 4, an 8, 16, 32, no 64, okay, no 128, and that last one right here is a 256 plus 256. Okay, now let me use my calculator to just see what those numbers work out to. Let me see, can you see those numbers? Yeah, you can. Okay, whoops, grab this, copy. All right, the top one is 367. The bottom one is 315, like this. And if I do 315 plus 367, that gives me 682. Okay, like this. This should equal 682. All right, and you ask the question, does it? Well, let's convert that bottom one, okay, because we're checking here, okay? So this bottom number here had better be 682, or else we did something wrong, okay? So there's no 1, there's a 2, no 4, and there's an 8, okay? So let's just start there. There's a 2, and there's an 8. Okay, so no 1, a 2, no 4, an 8, no 16, a 32. So plus 32, all right? So let's see, we were up here at 32, no 64, a 128, plus 128. All right, I've lost track here. So let's see, a 2, no 4, an 8, no 16, a 32, no 64, a 128. No 256, but this one, that last one there, that's a 512. Okay, so let's put in 512 like that. And let me just check that on my calculator. I think it worked. It looks about the right answer, but I'll just check it to make sure. Yep, 682. Okay, and so ta-da. So what did we just show? Well, whether you add the numbers in binary or you add the same values in decimal, you get the same answer, which you better, otherwise one system or the other is broken. Okay, so that's enough for the addition. Let me see if there's any questions in the chat. All right, so any questions so far? And I'll just get a drink of tea while I give you guys a chance to. All right, I don't see any questions so far, so let me move on. Again, I don't want to waste your time just waiting for the lag or whatever. All right, so the next one is multiplication, okay? And multiplication is also pretty easy, but long multiplication has both multiplication and addition, okay? So the four possibilities that you need here, they're just like these possibilities here. Okay, let me rewrite them, okay? Except that we're multiplying. We're multiplying. And of course, the answers are different. And you go, what's 0 times 0? It's just like it is in decimal. If you've got no nothing, you've got nothing. Okay? And if you've got no ones, then you've got nothing. And if you've got one nothing, you still have nothing. Okay, it's only if you have one that you have one. Okay, so it's exactly what you would expect. 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, and 1 times 1 is 1. Okay? And so there it is. There's multiplication. There is no carry. That's the point. There's no carry. You'll notice that is the total answer. All right. You don't even want to write in the carry, but if you were to write in the carry, it'd be 0. So actually, multiplication, 2-bit multiplication, is easier than 2-bit addition. All right. Anyhow, let's do a long multiplication. I don't want to do. I think I'll just do one of them. How about we do 1 1 0 1 1 multiplied by 1 0 0 1, like that. Okay. So this is long multiplication. So sometimes we usually like write a little multiplication sign over there, like that. And remember, like you probably did that in like grade 3 or something like that with decimal numbers, and now we're doing it with binary. Okay, and so you go, okay, let's multiply this number by this. But the multiplication is super simple in binary compared to decimal. In decimal, not only do you have to have like this huge multiplication table in your head, but you also have to worry about the carries and anything like that. In binary, no. If there's a 1 there, then 1 times that top number is just that top number again, because you get 1 times 1 is 1, 1 times 1 is 1, 1 times 0 is 1, 0, 1 times 1 is 1, and then 1 times 1 is 1. Okay, so basically when you multiply that one there by that entire number there, you just get that entire number. Whoops, that entire number. Let me try that again. There you go. You get that entire number. Let me line it up below the line. Okay, so how did I get that? Well, I just did 1 times 1 is 1, 1 times 1 is 1, 1 times 0 is 0, and then 1 times 1 is 1. And before you realize, go through the other, well, the last one is 1 times 1 is 1 here, like that. And you realize that 1 just replicates that entire number there. Okay, now if you do 0 times everything, you're just going to get zeros. So all of those digits just get turned into zeros. But since that's in the 2's column down here, you want to start in the 2's column. Okay, so you would do like 0 times 1 is 0 right here, like that. Okay, and then you go 0 times 1 is 0, and then 0 times 0 is 0. And before you realize it, you say, well, I'm just going to get, like that number has 5 bits in it. Okay, so right. It's 1, 2, 3, 4, 5 bits. And if you multiply each bit by 0, you're just going to get 5 zeros. And there they are. Okay, so there are the 5 zeros due to that one. And notice that I've bumped over to the left one space or one column, and that's because that 0 is in the 2's column, so you start that one in the 2's column. Okay, great. Well, you're going to get the same thing again with this one. All right, but now it's not going to be in the 2's column, so that would be in the 1's column. That's in the 2's column. Because that one's in the 4's column, you would start over here in the 4's column. Okay, so that 0 there, 0 times 1 is 0, and you put that in the 4's column there, and then you just get a bunch of zeros there again. Okay, and then that one is in the 8's column, so you just get that whole number there replicated, but it has to be moved over into the 8's column like this. Okay, and there you go. All right, so before I add everything up, let's just look at the pattern. If there's a 1 there in the 1's column, you just get all that number aligned with the 1's column. If there's a 0 there, well, then you get all those digits turned into zeros, but now aligned with the 2's column. That 0 there in the 4's column, all those bits there get turned into zeros, but now aligned in the 4's column. And that 1 there just replicates the entire number, but now it's replicated beginning in the 8's column. And there you go, everything's lined up. And now what? You just add. And where there's a blank here, like there's a blank right there, that blank is just 0. So that's like a 1 plus 0 all the way down. And then down here, you're going to get just a 1 like that. Okay, so that one there is just added to a 0 there, and a 0 there, and a 0 there. So it's like 0 plus 0 plus 0 is 1. Okay, and then the same thing with that one. That one's going to be 0 there plus 0 there plus 0 there. Okay, so that just gives us a 1 right there. And then that's a 0 there, a 0 there, a 0 there, and a 0 there, and that gives you a 0 there. Okay, and then here it gets a little bit more interesting. You got a 1 plus 0 plus 0 plus 1. And so 1 plus 1 is 0. So 0, carry 1. And you say, where am I going to put that carry of 1? I'm going to put that carry of 1 right there underneath it. Okay. So 1 plus 0 plus 0 plus 0 is 0, carry 1. Okay. And then I've got 1 plus 1 plus 1. And 1 plus 1 plus 1 is 1, carry 1. Okay, and then in the next column I've got all zeros except for that 1 carry there, so that's 1. Okay, and then the next column I've got just a 1, so there's a 1 there, and then the last column I've got a 1 there, like that. Okay, so it might be a little hard to see this addition because there are just so many blanks in there, but wherever you see a blank, just think of it as a 0. Okay, and some people learn to do multiplication to actually put zeros there, so you can actually put 0 there and 0 0 there, and then here 0 0 0 there, like that. Okay, if that helps. Okay, and then and then these ones, remember, are the carries. Okay, and so 1 1 0 1 1 multiplied by 101 is going to equal 1 1 1 1 0 0 1 1. Okay, and there's the multiplication. So on the test I'm not going to ask you to check, but why not, right? We're doing it together. 1 plus 2, so convert, right, to do the check. So 1 plus 2, no 4s, an 8, and a 16. So 1 plus 2 plus no 4s, an 8, and a 16. And let's see what's that equal to. I'll just use my calculator because I'll mess up otherwise. 27. Yeah, okay. And then the bottom one, that one I have memorized. That one is 9. And now if I do 27 times 9, that's going to give me 243. So this bottom number here had better equal 243. Otherwise, we did something wrong. Okay. So let's see if that's actually equal to 243. So that's 1 plus 2. All right. 1 plus 2 from those two. Okay. No 4s, no 8s. And then 16, 32, 64, and 128. Okay. So let's see here. I lost track. So 1, 2, 4, 8. So it starts with 16 plus 16 plus 32 plus 64 plus 128. All right, and that looks right. Let me just check on the calculator. Yep, it is 243. Okay, good. All right, so there you go. I'm not going to do another multiplication, and that's about as complicated as they are. The addition, I can make them big, like I can make them long because it's just like the same kind of like repeated pattern. With the multiplication, if I make them too big, you've got too many rows here. If you've got too many rows, then you can have carries which carry over 2 or 3 columns over. Okay, that's not something you see in decimal, but I just wanted to avoid that complication. So the numbers for the binary multiplication will be kind of smallish. All right, let me see if there's any questions. And all right. Okay. All right. So the next topic was binary logic, and there's 4 binary operators that you need to know. So when I say operator, all that means is like addition is an operator. It just takes 2 bits and it operates on them and makes them into 1. Okay. Well, in addition, it can make them into 2, but for multiplication, it makes them into 1. In fact, and multiplication and binary are the same thing. Okay, so here I wrote multiplication, but you could also write just and, because the way and works is it's 1 if and only if they're both 1. Okay, so here's how binary and works. Just think of them as like kind of an extension to your algebra, like all the algebra that you've learned, but now you've got these extra like operators. Okay, so with and, it's 0. The only way you're going to get 1 with and is if they're both 1. So 1 and 1 gives you 1. Anything else gives you 0. Okay, that is multiplication. In fact, you saw what I did. I just took the multiplication table here and replaced the multiplication with and we were done. So in binary, there is no difference between multiplication and and. Okay, we give them 2 different names because I don't know, because like because in decimal there is a difference. But if we were like binary creatures, if we grew up binary, we would never have had and multiplication. We would have just used the same name for both of them. Okay. Now the way OR works is a little different. I'm just stealing that table here. Okay. And let me get rid of these answers. And let me switch to OR. By the way, you don't just study this in computers. Okay, I don't know if any of you have taken any philosophy courses, but there's actually logic in philosophy. The same stuff is studied in philosophy as well. Okay, and that's because it's part of how you make logical arguments. Okay, so there's some overlap with other disciplines as well. All right. Okay, so with OR, if they're both zeros, 0 or 0, you get 0. If there's a 1 at all, doesn't matter if there's a 0, but if there's a 1, the answer is 1. Okay, so notice that with the and, they both have to be ones to get a 1. Okay, if either one of them are 0, you get 0. But with an OR, it's sufficient for one of them to be a 1 for the answer to be 1. Okay, so 0 or 0 gives 0, but 0 or 1 gives 1. 1 or 0 gives 1, and 1 or 1 gives 1. Okay, and that's how OR works. Okay, now the exclusive OR is like the OR, but what happens there is you can't have both ones. Okay, you have to exclude the possibility. Whoops, what just happened? You have to exclude the possibility of them both being one. So far, everything is the same as OR. Okay, all I did was just put XOR there instead of OR. But over here, if I put XOR, 1 exclusive OR 1 is 0. That's the difference. Okay, so whereas you have 1 OR 1 is 1, 1 exclusive OR 1 is 0. Okay, and the only other operator you need, binary operator, is not, and not is a unary operator. It just operates on one thing. So if you have not 0, it's 1, and if it's not 1, then it's 0. Okay, so it just flips it like that. Whoop, sorry, hold on, there we go. So not 0 is 1, and not 1 is 0. Okay, so that's all you need for the not operator. And I didn't say this, but I think it's obvious that 0 is like false and 1 is like true. Okay, so maybe we should just say that at the very beginning here. 0 is like false and 1 is like true. Okay, and now we've made the full connection to like a logic course in philosophy. Okay, and if you could just read it, and so like you can, instead of saying 0, you could just read it as false. If something is not false, then it must be true, and if something is not true, then it must be false. Okay, that's how these work. Okay, now why are these interesting? Well, they're interesting for two reasons. One, you can take any binary arithmetic and reduce it to logic. Okay, so you could take arithmetic and reduce it to logic, and I'll do that for you in just a second. But also, you can build machines that do logic, and that's what the gates are. And so this is kind of the crux of how computers work. Okay, this is kind of the secret. Okay, you have machines called logic gates which do logic, and logic can be used to do arithmetic. And so you can build machines that do arithmetic. And arithmetic, up until you had machines that could do arithmetic, was only something that you could do with the human mind. And so you've got a mechanical mind, a machine that does the same thing that the mind does. Okay, addition. Now, computers do a lot more things, but this is just a simple course. So I just wanted you to show you one thing that I could build a machine and it would do the same thing that the human mind does. Okay, so how is addition? Well, I showed you how multiplication is and. Okay, so if you say multiplication, I don't want to do multiplication. I say, okay, fine, just do and. But if I want to do addition, it's a little bit more complicated. With addition, you have two things. Addition, you have exclusive OR for the least significant figure, and you have and for the carry. Okay, so if you go back to this addition that we did way back up here, you take these here like that, and you say, okay, look at how on the right-hand side you've got two digits. Okay, and you go, well, what are those two digits? Well, let me call this first digit here, that one right there, or that one, or that one, or that one. Let me just call it A, because I got to give it a name. And let me call the second one B, that one, or that one, or that one, or that one. Let me call it B. And what's that going to equal? That's going to equal this first digit, okay? And that's what? That's the carry. Okay, so we'll call that C. And then it's also going to give you this last digit here. And what's that one? We called it the least significant figure. And we'll just call it L. And you say, is there a logical relationship between A, B, and C? How does A and B combine? How does A and B combine logically to give you C? Well, take a look here. Here's A and B, and here's C. Just ignore this other digit for now. Just ignore it, because we're just looking at C. And you go, oh, look at that. Only if they're both 1 do you get 1. Only if they're both 1 do you get 1. Only if they're both 1 do you get 1. And you go, the carry is obtained by AND. Okay, so the carry here is obtained from A and B by AND. And you go, what about the least significant figure? And now you do the opposite. Now you say, well, just ignore this one and look at that one. And you go, well, if they're both 0, you get 0. If they're both 1, you get 0. And only if 1 is 0 and 1 is 1, do you get a 1. And you go, what logical operator does that? And you go, aha, that's the exclusive OR. Because with the exclusive OR, if they're both 0, it's 0. If they're both 1, it's 0. Only if one is 0 and the other one's 1, do you get a 1. And you go, okay, so that tells me that A and B, oops, sorry about that. A and B, the way they combine to give you the least significant figure, they must combine using exclusive OR. And you go, okay, great. What have I done here? These two together are basically the exact same thing as addition. So addition can be replaced by exclusive OR for the least significant figure, and it can be replaced by AND for the carry. All right, there we go. So you say, well, what would I ask on a test? I would ask, what logical operators would you use to get the carry in 2-bit addition? Well, AND. What logical operator would you use to get the least significant figure in 2-bit addition? Exclusive OR. Okay, so that's the kind of question I would ask. Okay, and since it's multiple choice, I would give you all possibilities, some crazy possibilities, but you have to obviously pick. For the least significant figure, you got to pick exclusive OR. For the carry, you got to pick AND. All right, and so there you go. That's enough for logic, binary logic. All right, let me just take a look in the chat again. All right. Any questions? All right. Just give a second to see if anyone has a question. Otherwise, I'll just continue here. All right. So now, for the next one, you do have to know the symbols for and or exclusive or and not. Okay, now it's a bit of because this is open book, and you can use the website logic.ly/demo to do these, just like you did on your assignment. You can make use of that site. So I'm just going to make up a circuit and show you the kinds of questions that I could ask with that circuit. So basically here, I just want to see if you understand binary circuits. Okay, and let me just switch to there you go. So I've just switched to logic.ly/demo, and I don't know, I'm going to just make up a circuit. Okay, what should we use here? How about we use an AND gate, and how about we use an OR gate like that? Okay, something like that. And so you got to have some outputs here, and the light bulbs are the outputs like this, and you got to have inputs, and the inputs are going to be like my switches, and I don't know, let's do 3 switches. I mean, there's all possibilities, and I would give you this diagram. I would give you a diagram like this, and I don't know, I'm just making a crazy circuit here. I need another gate. Hold on here. How about another? Here, we'll just add an exclusive OR. Okay, let's do this, and then we'll add that, and then I guess I need another light bulb. Okay, and let's attach that one to that one, that one to that one, and that one to that one. Okay, let me see if you can see that pretty good. Okay, good. So I've got these 3 switches, and I wired them up in a kind of a I wouldn't say crazy, but a little bit of a spaghetti in there. And so you got to be careful, like just take a look at that first switch here, the top switch. You know what? I should label the switches. Let me label them. So where's the labels here? I would call this one like input A. So this one be like input A. And I'd have a label on this one. This would be input. Whoops, what just happened? Uh-oh. Oh no. Okay, there we go. I got it back. I lost the focus for some reason. So this switch would be input B. And then this switch here would be input C. And then this light bulb would be output. Output A. And this one is output B, and then I'd have another light bulb here, and that one would be output C, like that. Okay, and I would ask something like this. I would say input A is on, input B is off, and input C is on. Okay, So the question would say I have input A on, input B off, and input C on. What are the light bulbs doing? And you would have to say light bulb A is off. Okay, you can see it right here. Light bulb A is off, light bulb B is on, and light bulb C is on. Okay, and that would give you the right answer. All right, and then and another question. I think I've got three or four of these. I don't remember now. But in another question, I would say, okay, now I have switch A off, or input A off, input B on, and input C on. Okay, so A is off, B is on, and C is on. Okay, and remember with logic.ly, the way it works is blue means on. Okay, so you can see that blue outline there, that means on, and there's no blue outline there, so that means off. Okay, so A is off, B is on, C is on, and I ask you, what are the light bulbs doing? And you have to say, output A is off, output B is on, and output C is off. Okay, and to make sure that you get this right, that you don't confuse it, because if you're going to use this website, you don't want to confuse it. So make sure that you know what the symbols look like. That's the AND gate right there that I have highlighted. Okay, in fact, you know what? Let me get rid of everything. Let me just get rid of all this, and let me get rid of all this. Okay, that one, the top one there is the AND gate. I think I can make that bigger. Let me just make it a. How do I make this bigger? Whoops. There we go. That's a little bit bigger. So the top one here is the AND gate. It looks like a bullet. The next one is the OR gate, and then the one below it is the exclusive OR, and the NOT gate looks like this. Okay. It looks like that, and you'll notice it's a triangle, but it's important that you notice that there's a little like bubble at the tip of that at the tip of the triangle. Okay, the reason it's important to notice that is because there are also NAND gates and buffers and NOR gates and exclusive NOR gates, and they look almost the same. Now they're labeled right, but they look almost the same, and I want to show you what the difference is. So actually, let's get rid of those, and let me just show you the difference between, so you don't make a mistake, the difference between an AND and a NAND gate. Now we didn't study NAND gates in detail, although I'll show you. We did a little bit, but what's the difference? You go, geez, they look almost identical. Yeah, almost. The top one is the AND gate, and at the very end, where the output is, you'll see that there's no little bubble. Okay, and the bottom one is the NAND gate, and you'll see that there is a little bubble. Okay, so just be careful with that. I mean, this site is used to teach computers in a lot more depth than I taught you, and so they've got a lot more gates than what I expect you to know. So just make sure that when you look at the correct gates here, that you pick out the ones that correspond to the and not the NAND. They look similar, but as I just showed you, they are different. Okay. All right, so that's about it. For questions on binary gates and so on. I do expect you to know what you can, how they're built out of transistors. Okay, and so you do need to know that a single transistor. I'll show you a picture in a second. Let's get through this first. A single transistor is basically a NOT gate. It's basically a NOT gate. Okay. Two transistors in series. You say, what series? I'll show you the picture in a minute, but it's like one daisy chained after the other. One transistor after the other. Not side by side, but one after the other. That's what series means. So two transistors in series act like a NOR gate. And two transistors in parallel, that is side by side, act like a NAND gate. Okay? And you say, whoa, what's this NOR and NAND all about? Okay, because we didn't need them above. I know. But if you take basically a NAND gate and then you add to it a NOT afterwards. So you got a NAND gate, and then after the NAND gate, you do a NOT gate. A NOT NAND, it sounds funny, a NOT NAND is an AND. Okay? So basically, the way you create an AND, the easiest way to create an AND out of a NAND gate is to put a NOT after it. Okay, so you got a NAND gate, and you say, but I want an AND. What do I do? Just add a NOT after it. Okay, and same thing with a NOR. You say, I've got a NOR gate. I don't want a NOR gate. I want an OR gate. Just add a NOT to it, and you will get an OR gate. And that means that the AND gate is made up of 3 transistors. Okay, and the OR gate is made up of 3 transistors. by itself, just a NOR gate by itself is 2 transistors. Here, I'll write in the number 2. And a NAND gate by itself is 2 transistors, but to convert it from the NAND to the AND, you need a 3rd transistor, okay? And so that's why AND is 3 transistors and OR is 3 transistors. By the way, just to complete that, exclusive OR needs 4 transistors, okay? I didn't show you these because I really don't want to overwhelm you. Think of this as kind of like art appreciation. You don't have to be an artist. You just have to appreciate art. Just like computer appreciation. I don't expect you to build computers, okay? But I just want you to leave this course and have an idea of what this technology is all about, okay? All right. Okay, so let me just show you some pictures of those, okay? And let me switch to the other tab here. Here we go. Okay, so this picture here, is it showing up? Good. Yeah, that's the NOR gate, and that's in series. Okay, so 2 transistors in series, and you can see that one follows the other. Okay, so 2 transistors in series basically gives you a NOR gate. Okay, and the inputs there, we see input A and input B. Basically, the way transistors work is if you don't apply any electricity. Okay, if you don't apply electricity to A and B, the electricity will just flow through it, okay? So, leave A alone. Don't do anything to A. Don't do anything to B. Just leave the transistor alone, and what will happen is the electricity will start from this symbol right here, which is the ground, and it'll just flow through both transistors and out the output, okay? As soon as you apply any electricity to A or electricity to B, it kind of cuts off the electricity, okay, flowing through it. All right, it's kind of like squeezing a valve shut. So if there's voltage applied at A, if there's electricity applied at A here, well then the flow through A is cut off. Okay, and so that's how they're a switch, because either you're not applying electricity and there is flow, or you're applying electricity and there isn't flow, okay? And if there is flow, well, then the light is on, and if there isn't flow, then the light is off, okay? So there it is, that tiny little switch, okay? Very, very tiny, all right? So 2 transistors in series, one after another, gives you a NOR, and then 2 transistors in parallel, you can see them here side by side, this gives you NAND, okay? And you've got this NAND gate, and you go, but I want an AND gate. Well, then over here at the output, just add a single transistor, and a single transistor by itself acts like NOT, and here it is. I gave you that picture as well. The single transistor by itself here like that basically acts like a NOT gate, okay? And if you want this explanation later, because you're kind of maybe it's easier for you to read it, get it in your head by reading it, you could just read the explanation because I give it there, okay? All right, let's switch back. So basically this is how gates are made out of transistors, so you need to know that. Okay, and then I do want to get up to the full adder, and just to be very clear about what a full adder is. Okay, so you say, well, what's a full adder? It means a machine that can add this, that can do exactly what we did right here. Okay, now we got all the, here, I'll just cut and paste it. Here, I'll just cut and paste this part here. Copy. Like this. Suppose I say, look, I want a machine that adds this number here to that number there. Okay, so a machine that would add the top number to the bottom number is a full adder. Okay, and you say, well, how does that adder work? Well, you know what, let's actually work backwards here. Let's actually work backwards. So if you start from the full adder, you say, well, how do I make this full adder work? Well, the first column is the exceptional column because there's no carry. But you know what? I'm going to pretend that there's a carry there like that. You can always add a 0 there and pretend there's a carry, and it won't change the answer. So if I start with this first column, the ones column, I go like 0 plus 1 is going to be 0, and then we carry 1. Okay, and so we added 3 bits, and we got a least significant bit, and we got a carry. And then we go into the second column. We go 1 plus 1 is going to be 1, carry 1, like that. Okay, and what you're noticing is that each column is basically a 3-bit adder. Okay, so each column, so if you want a full adder, each column is a 3-bit adder with a least significant figure that forms part of the answer, but a carry which cascades into the next column. So that's why I said a full adder is basically 3-bit adder for each column with cascading carries. And what I mean by the cascading carries is this column here creates a carry, but that carry is put into the next column. And that column, when you add up this column, you're going to get a carry and it goes into the next column. And when you add up that column, it's going to get a carry, 0, carry 1, and it cascades into the next column and so on. So a full adder is basically a 3-bit adder for each column with cascading carries. Okay? So I expect you to know that. All right. Whoops, I didn't quite see that, but you can see it there. Just so a 3-bit adder. Okay. And now, what's a 3-bit adder? Well, a 3-bit adder is basically two 2-bit adders for the input bits, and then an OR to add the carries. This is actually the hardest of all the circuits to understand. Okay, I'll just very quickly show you a picture, but I think that's for the test. That's all I need you to know. That a 3-bit adder basically has two 2-bit adders to add in all the input bits. Remember, there are 3 input bits. Okay, so there's a 2-bit adder to add the first 2, and then a 2-bit adder to add in the answer from the first to the second, and then you get these 2 carries, and you got to combine them together, and the 2 carries are combined together using an OR. Okay, and let me show you how that works here, and I got to switch to this one right here. Okay, so a little hard to see, I know, but basically there are 3 inputs here. Those are the 3 bits that you're adding. Okay, and first you add 2, and the first 2 that you add are added together using that 2-bit adder there. Okay, and then what you get is basically a least significant figure from that right here. All right, a least significant figure, and you add in the 3rd bit. Okay, so that 3rd bit gets added in from the answer to the previous one. Okay, now these are 2-bit adders, so you get a carry. You get a carry from the first addition. All right, and you get a carry from the second addition. All right, so the first addition has a carry and the second addition has a carry, and you say, well, what do I do with those carries? You add those 2 carries together and you get your final carry right there, like that. Okay, so basically it's 2 2-bit adders to add in the inputs, and that'll give you the overall least significant figure. But then you've got these 2 carries, and you add them together with an OR gate, and that gives you the overall carry. And you might say, well, why don't I need a 3-bit adder? Sorry, why do I need a 2-bit adder to add the 2 carries? And that's because you get this funny situation where you'll never have that the 2 carries are both 1. Okay, you'll either have like 0 and 0, or 1 or 0, or 0 or 1, but you'll never have 1 or 1. And because you never have both of them as ones, it's sufficient to just use a single OR gate to add them together. I agree, that's kind of a really hard concept to get in your mind, but like I said, for the test, it's just sufficient for you to know that a 3-bit adder is a 2-bit adder plus an OR gate for the carries. Okay, and then how do you do the 2-bit adder? Well, the 2-bit adder, I kind of showed you that already. The 2-bit adder is basically just an exclusive OR for the least significant figure and an AND for the carry. Okay, and if we go back to this, we can actually go inside of one of these 2-bit adders, and so now we're looking inside that 2-bit adder, and you can see there's the 2 inputs. There's one input right here, and there's another input, and they're combined using an exclusive OR, and that gives you the least significant figure. The same 2 are then combined using an AND gate, and that gives you the carry. Okay, and that's how you do 2-bit addition. Okay, so this program doesn't go any deeper, but if you looked inside the exclusive OR, you would see 4 transistors, and if you looked inside the AND, you would see 3 transistors. Okay, and so there's like boxes within boxes within boxes. If you look down deep enough, they're all transistors at the very bottom. Okay, and so that's it. That's how a computer is made. And so I basically was able to show you how to make a full adder out of switches. Okay, and there you go, a thinking machine. Now, that could almost put like a line here, because that's kind of like the first part of the course. Okay, but the way things worked out, I had to move on to the next topic, and so there's a little bit more on the test than just the computing side of it. We're actually starting to get into the more practical part of it, and this is encoding. But before I jumped into encoding, I actually gave you this Moore's law, and Moore's law is really not a law. All it says is just how manufacturers have been able to improve on computer technology over the years. And Moore, who was one of the co-founders of Intel, basically said that that manufacturers will be able to double the number of transistors that they put on per unit area every 1.5 years. Okay, now he originally said 2 years, but it works out that the law is more like 1.5 years. Okay, so what does that mean? Every 18 months, every year and a half, manufacturers of computers are able to improve the technology so that you'll get twice as many transistors on the same size chip. Okay, and this gives exponential growth because first it's 2, then it's 4 times, then it's 8, then 16. So this grows pretty quickly, and that means that the computers today are millions of times more powerful than the computers of the 90s. Okay, like much more powerful. Okay, and Moore's law is kind of coming to an end. I mean, we're not going to be able to make the transistors infinitely small. The smallest you could ever make the transistor is the size of an atom, and you won't be able to get down that far, but like just as a theoretical limit, and the size of an atom is 0.2 nanometers. So that's where I made my mistake in the video. I think I said that the current size of transistors is 0.2. No, the absolute limit to the smallest you can make a transistor is 0.2 nanometers, and a nanometer is a billionth of a meter, and this is absolutely tiny. It's like unimaginably small. Today our transistors are about 2 to 1 nanometer in size, so you can see that they're really tiny. Okay, which means you can put a lot of transistors on a small little chip, which is why your phones are like basically computers. Okay, like those big desktops of the ages past are now like inside your phone because they've been shrinking. Computers have been shrinking. Now, the more practical repercussion of that is that basically if you buy a computer today, in a year and a half, it'll be worth half as much. Okay, why? Because the technology's doubled in that time. Okay, so if we buy a computer today and it's like, let's say it's you pay $1,000 today, and you want to sell it in 18 months, in a year and a half, you're going to be selling that computer for $500. Okay. And unless you find someone who will be willing to pay more, I don't know why they would, but then you wait another year and a half, and then it's going to be only worth $250. You wait another year and a half, and that computer is only going to be worth $125, and so it depreciates pretty quickly. Okay, from $1,000. So how many years is that? Well, this is going to be 1.5 years, and this is going to be another year and a half, right? So we're up to 3 years now, and then another year and a half, like that. And so in 4.5 years, you're pretty much done. Okay, that the price of that computer is pretty much worthless. $100. Okay, from $1,000 down to $100. Okay, and that's about right. Most people will change out their computers every 5 years, maybe 6 years. Okay, something like that. All right, let me see if there's any questions in the chat. Oh, all right. Let me continue here, and we're down to our last topic. Okay, encoding, and basically, encoding is just this idea that you have, up till now we've just been playing with numbers. Okay, but and I know computers are called computers, which means like working with computing, like a calculator, but they do a lot more than that. They work with like letters and text, but they also work with colors, they work with sound, they do all sorts of multimedia stuff. And so you wonder, well, how in the world is a computer just a bunch of binary numbers? It's all ones and zeros, and yet it can represent color on the screen. And this is actually very important. It's a very deep and important subject. It'll touch every part of your life. You have to think about this, like like suppose you're working in a doctor's office, okay, and you're looking at an X-ray. That X-ray is all ones and zeros, okay, unless it's the old school like photographic film. If it's a digital X-ray, that's all ones and zeros. Okay, there's an ultrasound, that's all ones and zeros. Blood work. Different levels, that's all been reduced to ones and zeros. It's all been reduced to digital. And you go, how in the world is ones and zeros able to represent everything? And basically the idea is making a mapping. And wherever you hear me say the word mapping, think of it as like a dictionary, where a sequence of ones and zeros is interpreted as something, okay, by the computer. So a particular sequence of ones and zeros is interpreted as a color. A particular sequence of ones and zeros is interpreted as a letter. A particular sequence of ones and zeros is interpreted as a sound. Okay, now I didn't do sound. I just did, alphabets, and I did a little bit of colors, and I stopped. But again, it's to just give you this kind of flavor for how digital technology works. Because in the future, you're going to understand that you've got this digital X-ray, and you'll be able to understand how much information is in this digital X-ray based on how many ones and zeros it takes to represent that digital X-ray. And that's actually what we're going to get to next. Okay, and so you're going to have a much better sense of like what it means to say something has like 5 megabytes of information in it. Okay, so you look at this X-ray and it has like 10 gigabytes of data in it, and you go, well, what does that even mean? Well, what it means is that it's far beyond the human mind's ability to process all that information. X-rays now are being processed by computers that will look for features that human beings are not able to see. Okay, and that 10 gigabytes is kind of the crucial number that tells you just how much information is in this X-ray. All right, so yeah, this is more important than you think. It sounds theoretical right now, but it's more important than you think, because it really does say something about like what the meaning of all this digital representation is. Okay, so a standard, or probably the better thing, I call it just a standard, but maybe standard encoding. What it is it's basically a mapping. It's a convention, okay, for mapping from binary numbers to data items. Okay, and a convention means that we all have to agree to it. All computers have to use the same convention, otherwise computers don't have interoperability. Okay, but all computers are going to interpret the same sequence of ones and zeros as, say, the letter A, or the same sequence of ones and zeros as the letter B, and then the same file on one computer will look have the same letter A as another computer, like that. Okay, so that's what a standard encoding is. It's basically a convention for mapping binary numbers to data items. Mapping is like, think of it as interpreting, okay, a sequence of ones and zeros. Now that interpretation is it's arbitrary. Someone has to create it from scratch, but once it's created, we all adopt it, and that's what makes it a convention. Okay, now it's arbitrary, but it's not totally, there's something you can say about this. If you have an n-bit encoding, that means you can encode 2 to the n items. Now that sometimes confuses students, because they're like, well, what does that mean? So let me give you a very simple example. Suppose I have a 4-bit encoding. Ask the question, how many items can you encode? How many data items? How many things can you encode with 4 bits? Okay, so that's the way I would ask the question, and the answer would be 2 to the exponent 4. Okay, now you should know how to do exponentiation, but that basically means 2 times 2 times 2 times 2, okay, which is 16. Okay, so if you had 4-bit encoding, you can label 16 different data items. Okay, such that 0, 0, 0, 0 is one item, 0, 0, 0, 1 is another one, and so on. Okay, you go through all the possibilities, there's only 16 of them. Okay, so here's another example, 24-bit encoding. Oops, 24-bit encoding. Okay, well, that's going to be it's going to be 2 to the exponent 24. You go, that's a large number, so you have to know how to do this on your calculator. So you take 2 to the exponent 24, and you get a number which is a little over 16 million, and here it is. Okay, by the way, on the test I might even say a little over 16 million, but there's the exact number there. I'll put some commas so it's a little easier to see. So with 24 bits, you can encode 16,777,216 different items. Okay, by the way, 24-bit encoding covers all the different colors that human beings can see. Okay, better be careful. Human sight is made up of 3 primary colors: red, green, and blue. Now you might have learned those primary colors a little different, but I don't want to get into art here. Those are the 3 different types of cones that we have in the back of the eye. We have cones that are sensitive to red, cones that are sensitive to blue, cones that are sensitive to green. Okay, so red, green, and blue. Each one of those takes 8 bits. So you say, well, how much do you need to encode the red level? 8 bits. How much do you take to encode the green level? Another 8 bits. A different set of 8 bits. And how much for the blue? 8 bits. So if you think about this, it's going to be 8 bits for the red, then another 8 bits for the green, and then another 8 bits for the blue. So 8 plus 8 plus 8 is 24 bits. Okay, so there you go. This is all possible colors. Just the primary color is 8. But because we see 3 primary colors, that's a total of 24. Okay, so just the red is 8. So any one of the primary colors is 8, whether it's red, green, or blue. All right. But altogether 8 plus 8 plus 8 is 24. Okay, so just be careful. And I'm very careful when I say color. I just mean all possible colors. Okay, or color. If I say primary color, then I'm talking about obviously a primary color. Okay, so just look for that distinction on the test, whether I'm asking for how many different colors, how many bits does it take to encode all colors, or how many bits does it take to encode just a primary color, okay, or a primary color, because there's 3 of them. Okay? By the way, just so you remember, dogs only have 2 primary colors, and bees have 4. Okay, so different animals see color quite differently than we do. Okay, a convention started right at the very beginning where 8 bits is called a byte. Okay, and usually when we talk about sizes of files, which we will see after the test a lot of, we don't talk about bits, we will talk about bytes. We'll still have to use bits every once in a while, like especially when it comes to data rates, but generally speaking, we work in terms of byte. But a byte is 8 bits, okay? So to say, 8 bits or to say 1 byte is to say exactly the same thing, okay? All right. Don't know what else to say. Now, Ascii is the oldest encoding there is, okay? The very first thing we had to encode was just English letters, all right? Now, there's not a lot of them, so we came up with 8-bit encoding, okay? 8-bit encoding, similarly, we can call it 1-byte encoding. So if I say 8-bit encoding or I say 1-byte encoding, I'm really saying the same thing. And with 8 bits, you can encode 2 to the 8. Maybe I should just write that in there. 2 to the 8. And you say, how big is 2 to the 8? It's 256, okay? That's a little bit of overkill, but it's better to do 8 than 7, all right? And so each ASCII letter is 1 byte in size, okay? Equivalently, I could say each ASCII letter is 8 bits or each ASCII letter is 1 byte, okay? So if I asked the question like this, I said, how many bytes does it take to encode this, this little sentence here, the red fox, like that? And excluding the quotes, okay? So I'm going to exclude that quote there, and I'm going to exclude that quote there, because they would each be a byte each. But if we exclude those, we say, how many bytes does it take? Each letter is a byte. For ASCII, each letter is 1 byte. So you just count the number of letters, and you count the number of bytes. But you have to be careful, because spaces count, and exclamation points count, punctuation counts, okay? So there's 1, 2, 3, 4. The space counts. 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so all in all, you can see there I've got 12 bytes highlighted, so it takes 12 bytes to encode that little sentence there. Okay, the next one I showed you was Unicode, and Unicode covers all human writing systems. Okay, and that's huge. And, so because it's huge, it's actually 32 bits. Okay, so it's 4 times bigger than 8 bits. All right, so it's 32 bits or 4 bytes. All right, so that means that each letter is 4 bytes, not 1 byte, as ASCII 4 bytes. Okay, and there, like it's any alphabet. So here I chose Greek, just to choose a different alphabet. There's like Cyrillic, like the Russian alphabet, Hebrew, Chinese, any of those. Each character is 4 bytes. Okay, so just count the number of characters, and so you go 1, 2, 3, 4, 5, 6, 7, 8. And you can see there's 8 characters. Okay, but that doesn't mean 8 bytes. It means 8 times 4, or 32 bytes. Okay, so that string is 32 bytes long. Okay, 8 characters is 32 bytes for Unicode. All right, and I think I already said this about the primary colors. There are 3 primary colors. Each primary color takes 8 bits, so that means that all possible colors is 3 times 8 for 24. Okay, so with 24 bits you can cover all colors, or with 3 bytes you can cover all colors. Okay, remember 3 bytes means exactly the same as 24 bits. All right, so here's an example, a picture, a bitmap. There are different ways of doing pictures, but we don't want to study them all. We just studied bitmaps. A bitmap is made out of pixels, those tiny little squares. Okay, each pixel, okay, is exactly 1 color. It's one and only 1 color. Now, if it's only 1 color, that means it takes, it takes 3 bytes to encode the color of 1 pixel. Okay, because 1 pixel is 1 color, and 1 color takes 3 bytes, or 24 bits. Okay, 3 bytes. Okay, and so if I tell you that a particular bitmap is 500 by 700 pixels, so that's like 500 rows. Okay, 500 rows, 700 columns. Okay, so if you multiply the 500 times 700, let's just do that part first. You do that, 500 times 700. That tells you the number of pixels, but each pixel needs 3 bytes. So you take the 3 pixels and you multiply it by 3 bytes, and that tells you the size of the file. Okay, so the kind of question I would ask is, how big is a 500 by 700 pixel bitmap? Okay, so when I say big, I really mean how much information. Okay, so how big is a 500 by 700 pixel bitmap? And the answer is 500 times 700, and then multiply by 3 because each pixel is 3 bytes, and that gives you this number here. Okay, and we could put some commas in there just so you could see that it's a little over 1 million. All right, bytes. Now that is the right answer, but that's not the way I would put the answer on the test. What I would do on the test is I would convert it using one of the metric prefixes, and we're going to have to get used to that because we're going to get some really big numbers in computers, because everything shrunk because of Moore's law. The numbers got, really big because the amount of information you could put in files got bigger and bigger and bigger over time. Okay, and so we went from bytes to kilobytes to megabytes to gigabytes to terabytes and so on. Okay, and so you need to know this table here. And I know there's a difference between metric prefixes and binary prefixes, but just know that there's a difference, but you don't have to worry about the binary prefixes. We'll just work with the metric prefixes because that's how we'll do our problems. Okay, all right, so 1 kilobyte is 1,000 bytes. Okay, so kilo is 1,000. Okay, and 1,000 megabytes, sorry, 1 megabyte is 1,000 kilobytes. Okay, and a gigabyte is 1,000 megabytes, and a terabyte is 1,000 gigabytes, and a petabyte is 1,000 terabytes. Okay, so each time each metric prefix goes up by 1. You start with a byte. 1,000 of those is a kilobyte. You have a kilobyte. 1,000 of those is a megabyte. You have a megabyte. 1,000 of those is a gigabyte. You have a gigabyte. 1,000 of those is a terabyte. You have a terabyte. 1,000 of those is a petabyte. Okay, and so we're going from small at the top to big underneath. All right. Also, just be careful. Capital B means byte and little b means bit. So this number here on the test, I wouldn't show you the number like that on the test. What would I do? Well, if I divide the number by 1,000, so I take this 1,050,000 like that, and I divide it by 1,000. If I divide it by 1,000, basically I'm just removing those last 3 zeros there like that. Okay. But of course, if I divide it by 1,000, I go from byte to kilobyte. Okay. So I was at 1 million bytes, a little over 1 million bytes, and now divide that by 1,000, I'm a little over 1,000 kilobytes. Notice that when I divide the number by 1,000, I bump my metric prefix up from byte to kilobyte. Okay, but we're not done yet because you want to keep reducing the number until you're between, like, you're bigger than 1 but less than 1,000. So we could divide by 1,000 again, and if you do, of course, every time you divide by 1,000, you move the decimal over 3, so the decimal is going to move to where that comma is there, like that. And so you get 1.05. But of course, if you divide the number by 1,000, you got to up the metric prefix by 1, and so you go from kilo to megabyte, like that. Okay. So make sure you know how to do that conversion. Okay. So that's it for the test. I hope this review helps. And we covered everything like in an hour and a half. The test itself is, I'll give you an hour and a half in time. It should probably take you an hour to do, but I'll give you an hour and a half, just so you don't feel rushed or anything like that. Okay. And let me see if there's any questions in the chat. Otherwise, we are done. And I see we're down to no viewers now. So that's okay. As long as you watch this later, I hope this will be helpful. Okay. And of course, you can always email me questions afterwards. All right.